Okay, so today we're going to start something that's a little bit different, but it does really rely on a lot of things we've already learned. Solving trigonometric equations today. So in other words, when you have a bunch of trigonometric ratios in a full equation and you're solving for the angle that is locked within them. So here's today's plan. We're going to solve for an angle in a trigonometric ratio using either inverse trig, which is what we would have used in previous years, or using special triangles, which is what we've been doing the last few days. We're going to solve for the values of angles when they're in trigonometric ratio as a part of a larger equation. So that's going to be actually solving an equation. And then the last thing we're going to do today is stating the general solution of a trigonometric equation. A general solution, by the way, is the values of all of the angles that make an equation true. Recall that coterminal angles are 360 degrees apart and they're functionally identical. That's going to come in handy today. Anyway, let's get started. What I'm hitting you with right off the bat here is a diploma exam question, and of course, this year, spring 2020, there isn't a diploma exam, so this might seem a little silly, but I actually really like this question, and that's why I'm giving it to you guys. So if you want to try this, just pause the video here, give it a try on your own, but otherwise, we're going to go through it together right now. So as you can see in the corner here, 68.5%, that's the percentage of students in Alberta that got this question correct. The question is saying if cosecant theta is 2 over root 3, where 0 is less than or equal to theta and theta is less than 2 pi, then theta lies in quadrant blank and cotangent theta is equal to blank. First of all, notice cosecant theta is 2 over root 3. Cosecant is the reciprocal of sine, so we can therefore say that sine theta is root 3 over 2 because they're just reciprocals of one another. And this should seem pretty familiar as being one of the side lengths on a special triangle, but we'll come back to that in just a second. The first thing that we should notice here is sine is positive, right? And sine is only positive in 2 different quadrants. So if we draw a unit circle here, we hopefully remember from the cast rule that CAST, that only in this quadrant, the A quadrant for all and S quadrant for sine, only in those 2 quadrants is sine actually positive. And if sine is positive in these quadrants, therefore cosecant must also be positive. So right off the bat, we know that quadrant 1 and quadrant 2 are the quadrants we must be in. So if we look back at the actual answers here, we know that B can't be an answer and D can't be an answer either. So this has now reduced it down to either being A or C. Furthermore, I think what we should do to figure out the other column here, because now we're just dealing with cotangent theta, I think we should actually set up a triangle with this in it. Now on a unit circle, sine is actually the value of your y coordinate. So our y coordinate is going to be root 3 over 2, which is pretty close to 1. That's right here. So then we can make a right triangle with that. Remember, on a unit circle, your hypotenuse is 1, sine is your y, so root 3 over 2. And of course, we have an x down here, but hopefully you recognize this as being one of our special triangles, so your x is actually going to be 1/2. Now, again, it's also possible that we were in quadrant 2, so it could have been here. I won't draw it a second time, but it's the same triangle. The only difference is x would be negative 1/2, okay? Now, what we're looking for is cotangent theta. And I want to remind you that cotangent is the reciprocal of tan. Now, tan theta, hopefully you understand, is opposite over adjacent. And therefore, cotangent theta is adjacent over opposite. Well, in this triangle here, we can see we have our angle down in the bottom corner. Our adjacent side would be 1/2, and our opposite side would be root 3 over 2. So we can say that cotangent theta is our adjacent side, 1/2, over our opposite side, which is root 3 over 2. Now this is a fraction divided by a fraction. We don't like doing fraction division, so we can actually change this to be cotangent theta equals the first fraction on the top times by the reciprocal of the fraction on the bottom. We used to call that keep, change, flip. So keep the first one, change it from a divide to a times, and then flip the bottom one. So this is 1 over 2 times 2 over root 3. When you multiply fractions, you just multiply the tops and multiply the bottoms. Hopefully you can see that the 2's are going to cancel out here. So this leaves us with cotangent theta equals 1 over root 3. And that's just in quadrant 1. If you did it in quadrant 2, the only difference would be your 1/2 would be negative. So it's either this or cotangent theta is negative 1 over root 3. Well, that actually takes care of our answer here, because in row C, you can see that cotangent theta is plus or minus 1 over root 3. So the answer here must be C. Moving on. So this is in the note work booklet that is posted on Google Classroom. It's on page 31. We're actually going to do most of this section today because hopefully it'll go pretty quick. Just a real quick reminder about the approximate value for angles. When you're given a trig ratio, you can find the measure of the angle by reversing the process. To find theta, you must use the inverse trig function, which is second button on the calculator followed by whichever ratio you're given. Basically, just use inverse sine or inverse cos or inverse tan to undo the trig ratio and find whatever the angle was equal to, right? So for an example, given that sine theta equals 1/2, determine the value of theta, assuming it's in the first quadrant. You can use inverse trig on this. You can literally just go inverse sine of 1/2, and that's going to spit out the angle, because the rationale behind this is if you do the inverse sine of both sides, the inverse sine of sine just gets rid of the sine, so then you're left with theta equals the inverse sine of 1/2. If you throw that in your calculator, you're actually going to find that the inverse sine of 1/2 is 30 degrees, and that is in our first quadrant. If it wasn't in our first quadrant, we would just have a reference angle here, and then we would just have to apply it to our different quadrants, of course, using that reference angle. Now, you didn't actually have to use inverse trig on this one. 1/2 being sine theta is actually part of our special triangles. You hopefully would remember that if this is your theta and sine is opposite over hypotenuse, and we can always assume our hypotenuse to be 1, at least with a unit circle. If sine is 1/2, then that means it's 1/2 over 1. So we have 1/2 here, and already this looks like one of our special triangles, so we can say that this side is root 3 over 2. So right off the bat, hopefully you'd remember that the side length of 1/2 is right across from an angle of 30 degrees. So hopefully you didn't even have to use inverse trig on this. But what I'm saying here is inverse trig is an option to find an approximate angle value, right? Now, ideally, you always want to be using special triangles if you can. But if you're given a question that doesn't use special triangles, you have no choice but to use inverse trig. Okay, moving on. So if cotangent theta is root 3, determine the value of theta given that 0 is less than theta, which is less than pi over 2. So in other words, we're in quadrant 1, because quadrant 1, of course, is between 0 and pi over 2. We're just dealing with radians this time around. So we're told cotangent theta is root 3. These reciprocal trig ratios, like cotangent, they're just annoying. When you don't have to use them, don't, right? You could change cotangent theta equals root 3 to just being tan theta equals 1 over root 3, because they're just the reciprocal of one another. Tangent is the reciprocal of cotangent, and cotangent is the reciprocal of tan. So you can just flip them around to get something a little bit more reasonable. Now, this right here is quite interesting, and I wouldn't blame you if you don't notice it, but this root 3 that's in here is actually part of special triangles. Now, you might say, well, wait a minute, special triangles has root 3 over 2. Well, you're right, but just got to keep in mind that this still is going to show up when we deal with tan, because tan, of course, is your opposite side divided by your adjacent side, right? Now, if you're not seeing that, I don't blame you. So what we'll do first is we'll just use inverse trig on this one. So if you use inverse trig, on this, take the inverse tan of, 1 over root 3. And I'm actually going to do this in degree mode, because in radian mode, you're just going to get a really awkward decimal. So if I do it in degree mode, you're actually going to see that we get something very familiar. In degree mode, you actually find that you get 30 degrees. Now, we can turn 30 degrees into a radian, because of course we want radians. It's giving us the angle in radians here. To turn 30 degrees into radians, you can just times by 2 pi over 360 and then reduce, or maybe even just realize that that's pi over 6 radians, okay? So in other words, given that we're in this first quadrant, if cotangent theta is root 3, therefore tan theta is 1 over root 3, that means theta equals pi over 6. Now I'm just going to come back to what I was alluding to before, about how this is actually part of special triangles. And clearly, when we did inverse trig, yeah, it totally is, because special triangles are those 30, 60, 90, or those 45, 45, 90 triangles. Here's how we could do this. Imagine we had our 30, 60, oh, that's horrible, my mistake. 30, 60, 90 triangle, let's say right here. We'll just do it in degrees just for the sake of easiness here. 30, 60, 90. We know across from 30 degrees we have 1/2, across from 60 degrees we have √3/2, and our hypotenuse, as always, is 1. If we're looking for tan of this angle, tan of 30 degrees is going to be 1/2 over √3/2. And like what we did earlier in that diploma exam question, you can just keep change flip. So if you keep change flip this, it's going to be 1/2 times 2 over √3, and therefore tan 30 equals, these 2's would cancel out, 1 over √3, right? So that is what we had started with up here, so therefore we can identify it from there. I would say for 99% of you, just doing inverse trig is probably way easier, right? Especially when you did it in degree mode and then turned it into a radian. Because again, if you had tried this in radian mode in your calculator, it would have given you this, but it would have given you that as a really horrible decimal number. It probably would have been like 0.5 something. I'm not 100% certain, but it wouldn't have given you a nice even pi/6. That's a good exact value that is a little bit more useful for us. So again, title kind of says it all. Use special triangles when you can. If you don't have to use inverse trig, don't. Okay, like I know inverse trig is pretty quick and easy and convenient, but if you don't have to use it, then don't, right? This next question is on page 32. The little top blip right here is just giving you a reminder. When you use inverse sine, cos, or tan on your calculator, you should always be given an acute angle. This is why I always suggest never plug in negative numbers in inverse trig. If you put in a negative number in inverse trig, you get some unpredictable answers. Just always turn it into a positive number. Like even if it gives you like, oh, take the inverse sine of negative 0.8 or something, right? Just turn it to positive 0.8 and then use that as a reference angle for any of the quadrants that it could be in. You got to remember your cast rule here, that generally speaking, if you have a positive sign, for example, it's going to show up here, but if you had a negative sign, it's going to show up down here. The same goes for tan and cosine. They're going to be positive and negative in different quadrants. Here's a good example of that. Cosine theta equals negative 0.5. Determine the value of theta given that it's between 0 and 2 pi. That, in other words, means it's anywhere in this full range, okay? Like the full 360, because 2 pi is 360 degrees. Hopefully you see that this is really negative 1/2. Negative 1/2 is, of course, part of our special triangle, so you don't actually have to use inverse trig here. Cosine spits out the x. So we're saying really x is negative 1/2. I'm going to ignore that for a second and just say it's positive 1/2. That wasn't exactly the greatest triangle either, but you know what, you're getting the idea. √3/2. There you are. So we're talking cosine, of course, is of this angle. Cosine is adjacent over hypotenuse. That's why I put this here. Well, when you're dealing with this angle and your adjacent side is 1/2, that angle is 60 degrees. Or in other words, in radians, that angle is pi/3 radians. Now, cosine is negative, so by the cast rule, we must either be in quadrant 2 or we're in quadrant 3, right? If we're in quadrant 2, what you need to do to find what your actual angle is, what your actual theta is, you're going to have to say that theta is 180 degrees, or in other words, pi, minus your reference angle of pi/3. Well, then that gives us theta equals pi minus pi/3. You can think of this as 3 pi/3 minus 1 pi/3. It's going to give us 2 pi/3. So there's one of our answers. But we could also be in quadrant 3. And in quadrant 3, you're going to want to go theta equals pi plus our reference angle. So plus pi/3. And that, of course, is going to give us 3 pi/3 plus 1 pi/3 is 4 pi/3. So just keep in mind, when you can use special triangles, please try to do it. But if you didn't know that this was part of a special triangle, you can always rely back on your inverse trig. Now, it's just nice to use inverse trig when you're dealing with degrees, because if you're dealing with radians, it can often give you a really messy number. Now, sometimes you have no choice, even with radians, to get a really messy number, because just sometimes that's how it works. Sometimes you're given a radian that isn't based around pi at all. But just keep that in mind. All right, so here's another example. If tan theta equals 5.24, determine the value of theta given that it's between negative 180 degrees and positive 180 degrees. This is a really ugly domain, right? Usually we say something like, oh, between 0 and 360, but no, they decided to throw some negative angles in here. Keep in mind the negative 180 degrees is like if you went backwards, or in other words, clockwise, back to 180 degrees over here, because that would be negative 180 degrees. And then if you came back up here and then flipped back over this way, it'd be positive 180 degrees. So we're still dealing with a full circle. It's just we're kind of calling it a different thing. Rather than saying 0 to 360, we're just saying it's negative 180 to positive 180. So I'll even write negative 180 here as well. So it's given us 10 is equal to this decimal number. Hopefully not a big surprise to you. There's no way you're going to use special triangles on this. 5.24, that has nothing to do with anything we've looked at. You have to use inverse trig. So let's just take the inverse trig on this one. We want our answer in degrees, which is quite convenient. So let's just stick in degrees. Inverse tan of 5.24. Just give me a second here. If you take inverse tan of 5.24, let's just say to the nearest tenth, you get 79.2 degrees. Now let's keep in mind what quadrants this has to be in. By the cast rule, tan is only positive in this quadrant and this quadrant, right? Now this 79.2 degrees is a reference angle, okay? You always get a reference angle by using inverse trig, especially when you take inverse trig of a positive number. This is our reference angle. If we're in quadrant 1, then our true angle is, well, it is our reference angle, so 79.2 degrees. So there's one of our answers. But keep in mind, we could also be down here in quadrant 3, right? Now there's a couple different ways we could do this. Usually in quadrant 3, we would say 180 degrees plus your reference angle. But if you added 79.2 degrees to 180 degrees, you're gonna get like 200 and something degrees, which is outside of this domain. So we actually have to do something that's a little bit different here. And just bear with me on this, because I know how stupid this seems, but it's just how these questions can go. When we're in quadrant 3, we're not actually going to deal with positive 180 degrees being what we add things to. We're actually going to deal with it being negative 180 degrees being what we add it to. Let me put it this way. Imagine our reference angle was something nice and easy, like 10 degrees. So we were just coming 10 degrees off of this axis. Well, that axis there, if we're going clockwise, is negative 180 degrees. So if you added 10 degrees to it, you'd be at negative 170 degrees as being your true angle, right? If you want to add 360 to negative 170, you'd actually see that it's equal to the same thing as 190 degrees. In other words, they're coterminal, right? And 190 degrees would clearly be your answer if we just dealt with a normal situation here. Long story short, just take your negative 180 degrees and add your reference angle of 79.2 degrees to it, and you're going to get your true angle of being negative 100.8 degrees. So those would be the angles that satisfy this equation given this domain. Next question here, if cosecant theta is 2 over root 3, determine the value of theta given that theta is between 0 and 3.14. Well, that's kind of suspicious. It's almost like that's pi or something like that, right? Cosecant theta, cosecant is an awful thing to work with. Let's turn it into something more familiar. Remember, cosecant is the reciprocal of sine, so we'll say that sine theta equals root 3 over 2. And what do you know? Root 3 over 2, that is a nice special triangle right there. If we were to draw our special triangles, remember sine of an angle, so sine of theta is your y over your hypotenuse, but we can assume our hypotenuse to be 1, so our y, of course, is root 3 over 2. And then therefore, that's a special triangle, so we know this side is 1/2. Now, when root 3 over 2 is your opposite side, that tells you that theta equals 60 degrees. But this clearly makes us deal with radians here, so we actually have to turn that into a radian. Theta is therefore equal to pi over 3, because that's the same thing as 60 degrees in radians. Now, we're just dealing within this domain. That domain is only these two quadrants. And since cosecant is 2 over root 3, and therefore sine is root 3 over 2, we know sine must be positive. Well, sine, by the cast rule, is positive also in these two quadrants. So in other words, this angle that we found, just using special triangles, is our reference angle, but we need to find what the angle is in both these quadrants. Well, quadrant 1 is kind of silly, because your reference angle is your true angle. So we can say theta equals pi over 3. There's an answer right there. But we could also be in quadrant 2, because sine can be positive in either one of those. So in quadrant, what am I doing here? In quadrant 2, there we go, theta equals pi minus pi over 3. which means that theta is 2 pi over 3. Hopefully this is making some sense to you guys. Hopefully this isn't just me rambling on. If you do have any questions, just send me an email. I know this is kind of bizarre stuff. Next up, solving a trigonometric equation. This is on page 33 in the note booklet. Solve this equation: 4 cosecant x minus 8 equals 0 over the domain 0 to 360. Finally, a normal looking domain, right? So in other words, we could be anywhere within this whole domain here. Basically, bottom line, when you're trying to solve a trig equation, you need to first get your trig ratio all by itself. Okay, so always get that trig ratio completely by itself first. To do that, let's just add 8 to both sides. 4 cosecant x equals positive 8. Then let's divide by 4, because that 4 is outside of your cosecant, so you might as well divide it away. Cosecant x is therefore equal to 8 divided by 4, which is 2. Now, cosecant is uncomfortable to us. We don't like dealing with cosecant. Let's change that into something a little bit more familiar. Cosecant is the reciprocal of sine, so we can say sine x equals the reciprocal of 2, which is 1 over 2. And what do you know? 1/2, that's part of special triangles here. Let's draw a special triangle. This angle right here, usually we call it theta, but they're calling it x. That's just really uncomfortable, but just know that x in this case is an angle. I know that just seems silly, but whatever. Remember that sine is opposite over hypotenuse. We always deal with our hypotenuse being 1 in this course, and that means it's 1/2 over 1, because sine is your opposite over your hypotenuse. And of course, a special triangle where you have 1 as your hypotenuse and 1/2 is your opposite side gives us root 3 over 2. I don't know why my 3's are so bad on this. There you go. Root 3 over 2 as being your adjacent side. So really, bottom line is here, we're looking for the value of x over this domain. We know sine x is 1/2. Well, the only time that we have 1/2 being across from our angle is if our angle itself was 30 degrees. Now that's just going to be our reference angle. So I'll call it XR. That's really uncomfortable to me, but you know what, whatever, deal with it. Really, we're trying to solve for this situation. And notice sine is positive by your cast rule. Sine is only positive in these two quadrants. So in quadrant 1, our answer is going to be our reference angle. So we can say x equals 30 degrees. Good. Quadrant 2, on the other hand, our x is going to take a little bit of work. Remember, we're up from the x-axis here. X is 180 degrees right here. So if we're going to subtract our reference angle from that, you're actually going to get 180 minus 30, or in other words, x equals 150 degrees. Whew, all right, almost done here, I promise. This example is also on page 33. Solve the equation 7 cos theta plus 5 equals 3 plus 3 cos theta within this domain. That's also a normal domain. It's from 0 to 2 pi, but it's just in radians, which I know might be uncomfortable for some of us still. Bottom line is, we want to get your trig ratio all by itself, okay? So the first thing I'm going to do is I notice I have 7 cosine theta here and 3 cosine theta here. Why don't I bring these 3 cosine thetas over to the other side by subtracting them away from both sides? If I take away 3 cos theta from this side, I have to take it away from this side as well. And that leaves us with 4 cos theta plus 5 equals 3. Let's move this 5 over now. So we'll subtract 5 from both sides. 4 cos theta equals 3 minus 5 is negative 2. Then let's divide by that 4. So cos theta equals negative 2 divided by 4 is negative 1/2. And what do you know? Negative 1/2, that's part of a special triangle as well. So with a special triangle, ooh, that's an awful one again. Let's try that again. There you go. Much better. With a special triangle, well, not much better really, that's, who am I kidding? With a special triangle though, where 1/2 is your cosine, this being our angle, cosine is adjacent over hypotenuse. The hypotenuse is 1, which just leaves our adjacent side as being 1/2 or negative 1/2 if you really prefer here. I'm just going to put 1/2 because I want to stick to positive numbers when I deal with this because I'm looking for a good reference angle. That means its opposite side over here must be root 3 over 2 based on your special triangles. And therefore, since cosine theta equals negative 1/2, that tells us that our theta, this angle right here, must be 60 degrees, or in other words, in radians, pi over 3. That's our reference angle, okay? Pi over 3. Let's now understand that we have to use our cast rule to figure out what quadrants we're actually dealing with here. So with our cast rule, notice that cosine is negative. That means we are not in this quadrant because everything is positive up here, and we're not in this quadrant because cosine's positive down here. So we must be either in quadrant 2 or quadrant 3. If we're in quadrant 2, we just need to use our reference angle to figure out what our true angle would be. Well, keep in mind that this is pi, so in other words, theta is going to be pi minus our reference angle, so pi minus pi over 3. Or in other words, theta equals 2 pi over 3. If we're in quadrant 3, on the other hand, then theta is going to be pi plus pi over 3. Or in other words, theta equals 3 pi over 3 plus 1 pi over 3 is 4 pi over 3. And there we go. Whew, that was a long lesson. I apologize for that, guys. But just to finish this off here, we have to talk very, very quickly about a general solution of a trig equation. This is also on page 33. Basically, a general solution just means that you're giving every angle that is coterminal to the angles that make up the solution, okay? This really literally is just the angle that you found, or the angles that you found, plus 2 pi n, where n is an integer. If you're dealing with degrees instead of radians, you say plus 360 times n, where n is an integer. What this is really doing is it's just adding or subtracting, because integers could be negative, it's adding or subtracting any possible multiple of 360 degrees or multiple of 2 pi to that angle. So it's counting for all of the coterminal angles, okay? Anyway, we'll determine a general solution to this equation right here. Remember, step number 1, get your trig ratio all by itself, so I'm going to minus 17 from both sides. 3 cotangent theta equals 29 minus 17 is 12. Divide that by 3, cotangent theta equals 4. Cotangent kind of sucks, so let's say this is tan theta equals 1/4. Well, that's not a special triangle, okay? So we have no choice. We have to use inverse trig here, so use inverse tan of 1/4, and you're going to find that theta rounded to the nearest tenth, just give me a second here, is, you know what, I think it actually just comes right on 14 degrees, okay? That's our reference angle, because again, we took the inverse tan of a positive number, that gives us a reference angle. Let's keep in mind what quadrant we're going to be in here. We weren't given a domain because we are given a general solution, which means we have to list literally every answer in existence. So if we think of our cast rule, tan is only positive in this quadrant and this quadrant. So in our quadrant 1, we have theta is just equal to our reference angle, so 14 degrees. In quadrant 3, we have theta is equal to 180 plus 14, or in other words, theta equals 194 degrees. But that isn't a general solution. There's only one more step you have to do to get a general solution here, and that's write it in this form, okay? Bear with me on this one. Your quadrant 1 solution is therefore 14 degrees plus, instead of 2 pi n, it's in degrees, we'll say 360 times n, where n is an element. I'm going to redo that little e thing, hold on. N is an element of your integers. That right there is one of your answers. In plain English, what this means is you have 14 degrees as your answer, but you could also add any multiple of 360 degrees onto it. So remember, if you added 360 degrees on a 14, that would give you like 374 degrees. 374 degrees is the same thing as 14 degrees. It takes up the exact same position. It's functionally identical, right? If you added 360 degrees again, so if n was 2, you'd add 720 degrees to it, it would give you the same angle all over again. That's a general solution. Let's do the same thing to our quadrant 3 angle. It's going to be 194 degrees plus 360n, where n is an element of the integers. So that right there would be your general solution. Just be mindful of that. If it asks for a general solution, it literally is just one extra step. It's just a matter of adding 360 degrees n, where n is an element of an integers, or if you're dealing with radians, you have to add 2 pi n, where n is an element of the integers. It's the same thing, okay? Anyway, now we're actually done here. For practice, I want you to do page 202, questions 10, 11, and 12, and then page 211, questions 1 to 6. As always, if you have any questions, please send them to me in either an email or a remind, or go ahead and post them on Google Classroom. Best of luck, guys.